Hello and welcome back to this video on damping in system models. If you've been following our videos up to this point, we've determined the output response of various systems when exposed to various types of input functions. When we've been doing this, we've been working in the S domain, and our transfer functions have been expressed in terms of S. And the general rule of thumb is where the transfer function only has S terms, it's a first order system, which has been derived from first order differential equations, whereas those transfer functions that include S squared terms represent second order systems. We saw examples of that when we derived transfer functions for ourselves in a previous video on second order systems. But in the following sections, we're going to apply the same methods that we did for first order systems to find system responses. And we're going to look at more examples, but this time for second order transfer functions. But before we move on to these, it's best to introduce ourselves to the topic of damping. So first of all, what do we mean by damping? Well, as a broader definition, damping is an influence to reduce or prevent oscillation in a system. For a very simple example, suppose that you're swinging on a playground swing. If you let your feet drag across the floor at each pass, you're introducing damping into the system, in addition to damping that's already present due to factors such as friction and air resistance. Second order systems will generally exhibit some form of damping, and we can categorize the amount of damping that a system exhibits into four categories. These are undamped or no damping, underdamped, critically damped, and overdamped. Here's a visualization of these types of damping on a graph. In later examples, when we come to derive system responses in second order systems, we'll see examples of these in practice. Let's first of all talk about what each of these means though. So first of all, an undamped system, or something without any damping, means that the system response doesn't decay and it doesn't tend towards a steady state over time. So in our diagram here, we can see that we have an oscillation that's just continuing indefinitely. And so the result is an output that's unstable, an oscillation or some kind of resonant effect. Generally speaking though, in practice, undamped systems are not observed in the real world. And the reason for this is because there's always some kind of damping or some kind of losses that are going to take place in systems, whether they be mechanical or electrical. So in a mechanical system, some energy is always going to be lost due to friction or heat in typical systems. In an electrical example, we're going to have resistive losses. So even electrical circuits such as oscillators or signal generators that produce sine waves, they'll require some kind of amplifier in practice because there'll be some small energy loss that needs to be overcome. An underdamped system is one where some damping takes place, but this damping is not enough to be classed as critical damping, which we'll talk about in just a moment. This means that some oscillation will still occur, but the system will eventually tend towards a steady state over time. So in electrical systems, this is often termed as ringing, where some oscillation will occur in a system, often following a step input or an impulse. In a mechanical system or a physical system, underdamped systems are naturally common because some small amount of friction or air resistance will cause small amounts of damping in nearly all systems. Imagine dropping a tennis ball which bounces off the floor, and with each bounce, energy is lost and the height of the ball gradually reduces with each bounce. A critically damped system is the most important on our list and is generally the form of damping that's ideal in most scenarios. So we define critical damping as the amount of damping that's just sufficient to prevent oscillation. And critical damping is ideal in most scenarios because it reaches the steady state in the minimum possible time. In mechanical systems, we see examples of critical damping in car suspensions. where we don't want the car to continue bouncing when travelling over a speed bump. That would be an underdamped scenario. Nor do we want the suspension to be displaced and take longer than necessary to return back to its normal position, which would be an overdamped situation, which we'll talk about in a second. Another mechanical example is a door closer mechanism, which closes a door gradually and prevents the door from slamming. It doesn't allow the door to swing freely, which would be an underdamped scenario, nor is it set to take the door hours to close, which would be overdamped. In electrical systems, we can also observe critical damping in RLC circuits under certain conditions, depending on the component values used, and we'll see examples of critically damped RLC circuits in later videos as well. Finally, overdamped systems are similar to critically damped systems in that oscillations are prevented. However, in contrast to the previous example of a critically damped system, an overdamped system takes a longer time to return to a steady state than necessary. In mechanical examples, overdamping is common in those systems that involve viscous drag or fluid friction. Imagine stirring a cup of treacle compared to stirring a cup of water or a cup of air. In electrical circuits, there are a few different factors that affect damping, but we can think of resistance as being like the treacle of our circuit, slowing the flow of current and increasing damping. By increasing the resistance too much, we risk overdamping our circuit response. It isn't quite as simple as this, but we'll see in more detail later in subsequent videos. For now though, let's summarise our findings here by visualising all four types of damping in this animation. The idea here being we've got these masses that are suspended from springs, and on the left hand side we have some undamped or example with no damping that will just continue oscillating indefinitely. Then we have an underdamped case where there's some oscillation, but that oscillation is diminishing over time and gradually approaching a steady state. We've got a critically damped example, which you'll notice is the first to reach the steady state in the minimum possible time. And then finally we have our overdamped example, which takes longer to reach that steady state. In the subsequent videos, we will see some mechanical examples, but we're chiefly going to be looking at electrical circuits, some of which we've already derived the expressions for, including RL, RC and RLC circuits. This topic of damping is going to become particularly relevant to those second order responses that we derived for series RLC circuits. So the RLC circuit was an example of a second order response, and we'll observe the different types of damping in RLC circuits in later videos. The type of damping in an RLC series circuit is actually determined by the relative sizes of the different components involved, and there's a good rule of thumb to bear in mind, which we'll refer to in later videos as well. So the conditions for an RLC circuit are these. If the response is overdamped, then R squared will be greater than 4L over C. So in other words, the value of the resistance squared will be greater than the value of 4 times the inductance divided by the capacitance. If the response is critically damped, we'll see that R squared must be equal to 4L over C. And finally, if the response is underdamped, then R squared will be less than 4L over C. You'll notice that an undamped response, or an example with no damping, is not listed here. The conditions for an undamped response are possible in theory, but the resistance would have to be 0. In practice, however, there'll always be some resistance in a circuit. Even capacitors and inductors have a small resistance. In reality, if we wish to observe an undamped response or an oscillation in an electric circuit, we'll require the use of an amplifier to compensate for the resistive losses in a circuit. So I hope you found this video on damping useful, but like I said, we will be looking at examples of underdamped, critically damped, overdamped system responses in the following videos, but we'll also be referring to some of the things that we've mentioned in this video as well.